Hello everyone, welcome to this session on GD&T and EZ Tol. Myself, Avichal from Softcell Technologies, and I'll be taking you through this session. We'll be talking about the relevance of GD&T and stack-up analysis or tolerance analysis, and then we'll look at how that can be done through Creo-based tools. So if you have any questions, please mention it in the chat box or in the Q&A section. I hope my screen is visible to you and audio is also clear. Can somebody please confirm? Okay, great. So myself, 𝐖𝐞𝐻𝐚𝐫 from Softcell Technologies, and here we are talking about how we can simplify GD&T application and also perform one-dimensional tolerance analysis with the same GD&T that we are applying on the CAD data. So before we get into the details about GD&T, let me give you a quick introduction about Softcell Technologies. So I'm from Softcell, and it's a 35-year-old company. We are working in engineering services division. There is also a system integration division, which is working with respect to the IT-related solutions. So in engineering services, we are primarily working with PTC. Somebody just mentioned that I'm not audible. Please, if you can check your audio settings, because I believe rest of the guys are able to hear me. Okay, so we are primarily working with PTC, which is one of the leading softwares in manufacturing industry. PTC is the company which has developed earlier. It had developed the software called Creo Wildfire, which was widely used for product design in various industry segments. Now it's renamed as Creo. So in PTC, we are working with respect to CAD, PLM, AR, and IoT solutions. So CAD obviously is for the product design development. PLM is for the product lifecycle management for the complete life of the product, starting from requirements all the way to the end of life of the product. And then augmented reality is through the Foria platform, where we are helping customers with augmented reality-based experiences for marketing service use case. Then IoT through ThingWorks platform for smart products and smart manufacturing. So these are the four Sigmetrics is for the 3D tolerance analysis through 𝐶 Tol, and also EZ Tol, which is a one-dimensional tolerance analysis tool from Sigmetrics, right? And then ANSYS, as you're probably aware, with respect to different kinds of simulations like structural, thermal, CFD, electromagnetics, light simulation. Okay, so we're working with these three OEMs and spread across these locations in India. To add some accreditations, we are platinum partner with PTC, also certified implementer for the PLM solution venture, and exclusive partner with Sigmetrics in India. Now, I'll just talk a little bit about Sigmetrics as a company also, because the tools that we are going to talk about in this session are developed by Sigmetrics. So we should give some credit to Sigmetrics also. They are it's a US-based company basically, and they are the global experts in GD&T and mechanical variation. And 𝐶 Tol is the main 3D tolerance analysis solution that was developed by Sigmetrics. Actually, it was developed by Texas Instruments, which is now called Raytheon. It's a defense company in US, and they are working on guided missile systems, and they wanted to increase the precision of their product. That's where they developed this tool, and then later Sigmetrics as a company was formed, and this collaborated with these CAD platforms, including Creo, to have the compatibility of the tool with these CAD platforms so that more and more people can use it. And apart from the tool, Sigmetrics also provides trainings for GD&T as per ASME ISO standards. Some other training programs are available like fundamentals of tolerance analysis, model-based definition or model-based enterprise. So this is a separate topic. I'll not get much into MPD process as such, but I'll just talk about how GD&T can be applied, which will also implement your MPD initiatives. Okay, so this is the portfolio from Sigmetrics. This session is focused mainly on one-dimensional tolerance analysis through EZ Tol, which is available as an add-in module in Creo, and then also GD&T Advisor for the GD&T application on CAD data in the 3D environment. EZ Tol is basically for the complete 3D based tolerance analysis, but we are focusing on EZ Tol and GD&T in this session. So if you are interested in the 3D based tolerance analysis tool EZ Tol, we can have webinars in the coming months and we can attend that for more information on it. This question is frequently asked by people as to why we need a 3D tolerance analysis tool, not a 1D analysis tool. Like, what is the difference? This is a this is a bifurcation. Like, if you are working on smaller assemblies with simple assembly constraints, the 2D, 3D variations may not be very significant. So there, 1D analysis tool like EZ Tol can be utilized. But as you move towards larger assemblies with more complex constraints, then a 3D tool like EZ Tol will become a necessity. And again, like depending on your product line, we can discuss in detail on one-to-one basis how which tool will actually be more helpful in your case. So coming to GD&T now. So we are talking about GD&T because GD&T approach helps in the design process by applying functional tolerances. Okay, and as you know that the product complexity is increasing. Also, there are in India, many companies are now working with global teams, so they have to adhere to the global norms for tolerancing also. And the very basic reason for GD&T is that there are certain limitations with respect to classical tolerancing, and with symbolic tolerancing, or you can say geometric tolerancing, those limitations are resolved. So helps you with the MPD process. So MPD is basically where you have the 3D CAD data as a single source of information. So most companies are still managing 2D and 3D. So they make 3D design and they make a 2D drawing from it. And then whenever they make some change in the 3D, they have to make sure that the 2D is always in sync. It is always getting updated along with the 3D. So they have to maintain two files and always have to ensure that they're in sync. So with MPD process, you can get away with 2D drawing altogether. So the 3D data itself will have all the dimensions, tolerances, GD&T, everything that is supposed to be there on the drawing. All the PMI, product manufacturing information, can be defined on the 3D data itself. So the same data can be developed by the design team and utilized by manufacturing, inspection, suppliers, everybody in the downstream delivery. Now, one hindrance, for the GD&T application is lack of expertise, and many of the companies in India still are struggling with this issue that they may not have GD&T expertise, in the complete design team. So they may have few experts, but rest of the people will be struggling because they're not experts in GD&T. They may have some basic understanding of it, but they don't have thorough knowledge, so they can still make mistakes. Okay. So what ends up happening is that GD&T application becomes complicated. Okay. And many companies, this is based on some survey where companies have mentioned that they want to use GD&T, but they are not able to utilize it because of either lack of expertise or lack of process defined, to implement GD&T. And then again, people with, you know, intermediate knowledge of GD&T, they start arguing about what is right, what is wrong, which symbol should be applied in which feature. So those things become problematic when you GD&T throughout your engineering process. Okay. Now coming to, so 80% of the companies are still struggling with respect to improper use of GD&T. Now with GD&T Advisor, so GD&T Advisor is basically a add-on module within Creo, where you can apply GD&T directly on the 3D data. The interface which you can see right now on the screen. This is provided to the user to give him a guided workflow so that he can apply GD&T more accurately. And the basic problem of implementing GD&T is that people make mistakes. They may select a wrong symbol, or they may select a wrong surface while applying the GD&T annotation. And multiple engineering changes are required. Some expert has to go through those drawings and then rectify all the mistakes, and then it has to go back and forth between the design process. So that takes a lot of time. Time cost for the company is actually impacted by that. So GD&T Advisor gives a guided workflow where you can apply GD&T more accurately. Even if you are not an expert in GD&T, you can, with basic understanding, you can still apply GD&T more accurately, and it will help with reduction in number of engineering changes going forward in the design cycle. So what you see on the left side, this feature tree, this is similar to your model treating your CAD 3D data. So this will generate features with respect to all the GD&T applications that you are defining. So for example, if I'm adding this whole feature as datum A, the surface is datum B perpendicular to A. So all of these will be added as features so that I can go back and edit them or redefine them at a later point. And then we also get this advisor tree, which will show information messages in terms of error or warning. If you, for example, if you miss out on some feature, if you don't define the feature completely, if you're defining it partially, let's say you're defining the location of a feature but not the orientation. Okay, so then it will show some error messages so that you can verify that everything is complete. Then we also get this constraint state where we get these different colors for different features. So all the features which are currently fully defined are shown with green color. The ones which are partially constrained are shown with yellow color. And then the unconstraints are obviously with the gray color. So that's how you can ensure that all the features are complete while applying GD&T. And even if you're continuing from if you start working on somebody else's data where they had started working on the GD&T application, but they have to leave it somewhere in the middle. So you can continue from there without having to check with the user as to how much of the work is done there. Okay, so let me take you to the software now and show it to you live. So we have this is the Creo interface. So please mention your queries in the chat box or in the Q&A section. So I'll be reading out those queries in between, and I'll try to answer them as much as I can in the session itself. Okay, so here we have a wheel assembly. Okay, so I'll quickly just explain what we have here. We have this top plate as the first part, top plate. Then we have axle support on one side, which is resting on the top plate on the surface. Then we have two screws which are bolted here, and that will constrain the axle support with respect to top plate. Okay, and then we have, these are the two screws, and then we have this bushing press fitted into the axle support. Okay. Likewise, we have the same set of parts on the other side, axle support, two screws, and then one bushing. And then we have this axle assembled in the middle, going through both the bushings. And we have this wheel assembled on top of the axle. And what you see here is some GD&T annotations which are displayed. So I can hide the annotations from here. So these are the GD&T annotations which are already applied. So for example, if I look at this top plate, here we have the GD&T annotations in 3D data. So for those of you who have used Creo earlier, you might have seen that there is this option called annotate, this annotate tab. So this tab can also be used for the GD&T application, but it has some limitations. So I'll just talk about that also. But before that, let me just start with the GD&T Advisor. So when we go to the Applications tab, GD&T Advisor, so here we have the tab wherein we can start this GD&T application. So now we have the GD&T Advisor tab open, and we have these options for applying GD&T. Then you can see that on the left side we have this feature tree. We have this feature tree showing all the datums. So this is my primary datum A, which has a flatness also. Then we have the secondary datum B, which is perpendicular to A within the tolerance zone of 0.1. Then we have datum C on the left side, again perpendicular to both A and B. These two surfaces which are in contact with the axle support. JSMD, we have this axle support in contact at these two surfaces. So let's say we want to define some control for these surfaces also. And then we have all the whole features wherein we can define some position tolerance. So again, when we get to it, we'll see what needs to be done there. So what I will do is I'll just delete everything so that we can start from scratch. So if this annotate tab is also there, so let me just quickly show what this annotate tab does. So here also we have options for applying GD&T, geometric tolerances. So let's say if I pick geometric tolerance button and then apply a tolerance here. So you can see that there is a position tolerance applied on this surface, position tolerance of 0.2 with respect to datum ABC, but there are no datums defined. So obviously this annotation based application is not correct because it doesn't really give you a guided workflow. Really, we should be it should be asking you to first define datums ABC, then only you can apply this. And then I'm applying position tolerance on this surface. So again, I can apply any of the geometric symbols without the tool helping me out. Okay. So that's the limitation. So I'll delete this and now we'll move to the GD&T Advisor option. So in GD&T Advisor, we have both ASME and ISO standards compatible. So here we have options for ASME by 14.5, 2009 and 2018. Both the versions are applicable. And then from ISO also we can apply. So let me just quickly show you where we can do that. So if I go to the product properties, here we have the option for changing the tolerancing standard from ASME to ISO. Okay. And then I can also change the standard version, let's say from 2009 to 2018. Okay, so these, this GD&T Advisor application is based on ASME rules. or ISO rules. So it will follow some of the rules which should be applied, which you may or may not be aware of. So we can, while working on it, we can actually identify that what are those rules. So for example, if I start with this tolerance feature on this top surface, okay, so I'll select this surface, and then it will ask me to apply flatness by default because it's a very first feature, primary data. So it's not asking me to apply any other data. In fact, it is disabling all the other features. So I cannot apply position, concentricity, orientation tolerances like perpendicularity, parallelism, position tolerance. So I cannot apply any of those. I can only apply flatness or profile. Okay, so that's the reason it is, like that's how it is going to help me apply only those annotations which will be applicable for that kind of feature, for that surface. So when I add some flatness, right now you can notice that this is yellow colored, so this is not defined right now. So if I put some value here, then I can press OK, and then the annotation will be added. So this is datum feature, and the tool also expects it to be a datum feature, so that's why it is pre-selected. The label, I can change the label if I want to. So there we have the datum A defined here with respect to flatness of 0.05. Now this surface is supposed to be my datum B. So when I go ahead and select this, now again you will see that because this is perpendicular, perpendicularity is the one which is suggested by the tool. So this asterisk symbol, it is suggesting that this is the best option. Although I can apply profile also, that would not be incorrect, but perpendicularity is the best option here. And again, you can see some of them are not applicable, like cylindricity or circularity cannot be applied to a flat surface, right? Flatness can be applied. So that's why it is going to disable some of those annotations. So when I put some tolerance value, now it's pre-selecting that datum A because datum A already exists. So it is assuming that this should be considered with respect to datum A itself. Now this perpendicularity of 0.1 with respect to A, that is added here for datum B. Okay, and then this side surface will become datum C. So again, I'll put some perpendicularity value with respect to A and B. Now let's say for these, for this surface, I go ahead and apply. Now we can apply profile, which will control all the variations for this surface. Like a flat surface can have two rotations. So it can rotate in two different directions and it can translate in vertical direction. So those are the three variables you can say for this surface. So the profile tolerance will control all three. Okay, so that's why this is suggested. Although parallelism can still be applied with respect to A. So right. So here we have parallelism applied on this surface. So this is going to control only the orientation, right? Not its location. So if I look at it in the advisor tree, it is giving me one error message that for this surface, location is not constrained. So this will give me a quick check as to which all features are partially constrained or which I forgot to constrain, or I'm not constraining them by mistake. So this will give me a uh, quick check about all those messages. Through all these messages, it will let me know what all features are partially or fully unconstrained. And if I click on this option, show or hide constraint state, I can see that all the green feature surfaces are fully constrained because those are the data features. And then this surface is shown in yellow color because this is partially constrained. Okay, so green is for fully constrained, yellow for partially constrained, and the gray one is for unconstrained. So all the rest of the features are gray because currently they are unconstrained. Okay, so now if I go back to this and change it from parallelism to profile, show constraint state, then it will show it in green color because it is now fully constrained, and that message is also because now it is controlling the location as well, not just the orientation. Okay, so now I'll go ahead and select this whole feature and apply some tolerance over here. So as I'm going to apply for tolerance for the whole feature, I can see that these are the various options which are applicable. I can apply salinity also in terms of form tolerances. So in terms of form tolerances, I can apply salinity, but position is the one which is the suggested one, which is going to control all the variables for this feature. Okay. Now let's say I don't want to define position tolerance for just one hole. I want to define it for the complete pattern for all the 4 holes. So I can go to tolerance pattern and then I can select all the 4 holes. Okay. And then I can apply position. Say 0.3. Here I also have option for adding material condition, whether maximum or least material, or RFS, regardless of feature size. Okay. And once I click OK, now I have the position tolerance defined. 4x is because we have 4 features here, so 4x. Then we have the size, nominal size, and then we have the position tolerance. 0.3 diametrical tolerance zone, 0.3 position tolerance with maximum material condition. But again, we have some error message here. That's because we have not, or let's say the user forgot to define the size tolerance. Now this is telling me that 0 tolerance value is not allowed. Now I may not know why this is not allowed. Okay, so as a user, I may not know the reason for it. So I can also click on it, help, go to help, and then get more understanding of it. So as per the ASME rules, 0 tolerance for size is not allowed. So now if I go to this and edit the diameter, it says symmetric plus minus 0.05. So now the tolerance for the size is added, and then that message is also removed because now that's not a problem anymore. So again, if I click on show constraint state, I can see all the green features which are fully constrained. Now for all the other features which are not critical, okay, so I can select multiple features also. Let's say if I want to select all of these surfaces which are not currently constrained, let's say select this one also. Right, so I can select all of them and give a general tolerance. So I'm just selecting all of them and just going to give a general tolerance, let's say 1. So now this is basically for all the 7 surfaces. 7 different surfaces have a general tolerance of profile of 1. Okay, so like this I can give tolerance to all non-functional features in a single group also. Okay. Also there is an option where I can add a note. So here we also have an option where we can simply add a note for general group. Just like we do it in drawings, we can simply say that for all the other features which are not defined, which don't have a GD&T annotation applied to them, there I can just put a note. Okay, and then all the surfaces which are shown in blue color, those have general profile tolerance. So this way I can apply general tolerances for all the non-functional views. These are shown in blue color, as you can see. Okay, now let's say for the tolerances that I'm applying, let's say in this case, I have, by mistake, let's say by mistake, I put a value of 3.0 instead of 0.3. Okay. So then again, it will show me some uh, error message that this value exceeds the maximum limit. So I can also put some limits as to what would be the maximum tolerance, geometric tolerance that we can apply. So here I have a limit of 1. So obviously if it exceeds that value, then it will again highlight that mistake. Okay, so that I can go ahead and change it. And obviously those limits are, these are the default limits. I can change these limits also. If let's say I'm working on sheet metal parts where I have larger tolerances, I can change the limit as well. If I change it back to 0.3, now that message is gone and the repository is actually empty right now because all the features are defined. So this will also help me, this constraint state will also help me start off from somewhere in the middle. Let's say somebody has worked on this part, he has defined the data, and I have to continue from there. So I can quickly see what is done, what is not done in terms of constraining the features, and then I can continue from there. So guys, if you have any questions, queries, please mention in the Q&A section or the chat box. Okay, so I'll just go back to the slide. Okay, so we have talked about the GD&T application in the CAD data. So these are the slides just showing the same thing that we have seen in the software itself. If you have questions, please mention in the chat box or Q&A section. You should be able to see it. I think that there should be a toolbar at the top which will show the options for mentioning something in the chat or Q&A. So you can just scroll through that. So basically, these are the benefits for using GD&T Advisor. First of all, it is based on the industry standards like ASME or ISO. So in a way, it will automatically take care of some rules which you should be following without even knowing those rules. You can continue with your work, and then the tool will be able to help you through that. Now, if the engineering team doesn't have expertise in GD&T, if they are having basic understanding of it, they can still start working and they can learn while they are working. So that way you can apply GD&T more accurately, efficiently, and then you don't have to go through all the GD&T learnings before you start working. Right. And obviously, the error reduction, because the tool is guiding the user, will help you reduce the errors as well. Now coming to the next topic, which is tolerance analysis. So this tolerance analysis in Creo is done through EZ Tol, which is a one-dimensional analysis tool again working at a plugin module in Creo. Okay, so let me again go back to the slide. So what I'll do is I'll just use the same example. The same assembly, caster wheel assembly. And what we'll do is we'll check the variation of the axis of the bushings. So we have to assemble this axle here, right? So we want to see what will be the variation between the axis of the bushings. Okay, between these two bushings. What is the axis variation? Let's say in vertical direction. And that will help us understand how much variation will be there for the axle, like how much tilt will be there for the axle. And obviously, if the axle is tilted, the wheel will also be tilted with that. So we want to minimize that. Okay, so that this is one of the objectives that we want to check. So I'll go to the Tol application now. Next to GD&T Advisor, we have EZ Tol. Okay, so we just hide this one now. So now I'll start defining the stack up chain. Okay, so I'll go to new stack up and simply select the features. And this is the gap. So basically it is between these two bushings, now with nominal gap of 0 mm, and then I can check the, like obviously my objective is to check what is the worst case or statistical variation for that gap. Now the tool will automatically define the stack up loop. So here it is saying that we have this bushing assembled in the axle support. Axle support is in contact with the top plate, and then the same set of constraints on the other side. So based on the assembly constraint that I've already defined in Creo, while putting the parts together, I've defined some constraints. So it is just following those same constraints and then defining the stack up loop. So if the assembly constraints are correct as per the actual physical assembly, then I can just use the assembly constraints and automatically define my stack up chain. But if that is not the case, if let's say you have assembled the parts using coordinate system, for example, or you have a step file or IGS file as an input where you don't have assembly constraints at all. So in that case, you can define the stack up chain manually. So I'll just show that process. So here we have pushing, the left pushing, which was the starting part, starting reference, which is transparent as you can see. So now I can select the next part. Okay, so I'm just selecting all the parts in the stack up chain, and now I'm selecting the references. So I've selected total 5 parts and 8 mating surfaces. So now when I press OK, the stack up table is created. On the right, you can see the stack up table showing the all the parts. Starting with the bushing, we have with the bushing we have the whole feature. That is my starting part. Looking at the axis for this hole for measurement. So this has the size variation, which is already defined in Creo, which is automatically taken as input here. Then we have the hole to the outer diameter for the bushing. This is the hole. As I'm scrolling through it, it will highlight it in this green color. So this is the hole, and then we have the outer diameter datum A, and the geometric tolerance of runout of 0.1 is defined in Creo annotation, like using the GD&T Advisor, which we have already seen. So this is the location, basically the orientation or the location for this whole feature with respect to datum. So that is the first input. Okay, from this part. Now we get to the next part, which is axle support. So here we have datum D, which is the whole feature, size variation for this hole, and then the position tolerance for this hole with respect to datum A in that part. Okay, so this is datum A, which is in contact with the top plate. Okay. And then we get to the top plate. So in the top plate, we have space 9, which is in contact with the axle support. This is the dimension 12 plus minus 1. So we have linear tolerance here. And then we get to datum A. Then the same dimension when we move down on the other side, data A to base 10. So here we have a linear tolerance, but if I want to apply geometric tolerance, I can apply it here itself. So let's say I put a tolerance of 0.3, profile of 0.3. With respect to datum A. Okay. Now coming on down on the from the right side, we have again the axial support and the bushing, and then finally we have this measurement with the nominal dimension of 0. And here I can put the objectives, like what is my design specification. Let's say I want this gap to be maintained within plus minus 0.3 mm. Great. So here at the top we have all the different types of results. So if I start with the worst case, here we can see that the worst case change the so we can see that the worst case can go up to plus minus 0.45. Okay, and my specification was 0.3. So the part of the worst case variation which is lying within my limits, that is shown in green color, and the rest of it is shown in red, which is outside of it. So that's how I can see like whether my objective is fulfilled or not if I'm looking at worst case variation. But let's say I'm more concerned about statistical variation because worst case may be too extreme, right? So worst case will happen only when we have all the dimensions pushed to their extreme value, but that has very small probability, right? So if I look at the statistical variation, here I can see that if I put some target for the statistical variation, let's say I'm looking at the sigma results. So my target is 4 sigma, for example. So 4 sigma is actually pretty close to my limit of plus minus 0.3. But let's say, for the sake of checking, let's say my target is 0.25. So then I can see that the 4 sigma and my objective is 0.25. So obviously it is going outside of that limit. Or in some another way, what I can see it says that the quality that I'm getting here, predicted quality, is 99.9%. So there is a failure of 0.1%. So if I'm making 1,000 assemblies, one of them will be having more variation than 0.25. Right. Let's say my target is even lower than that, 0.2. Then if my specification limit was 0.1, then it is only covering 81% of the yield, meaning that 19% of the assemblies will have more rejection. It will have rejection. So either they will have variation in the plus side more than 0.1 or less than minus 0.1. And I can also look at other results like defects per million. So right now what we have is 185,000 defects out of 1 million. So if I'm making 1 million assemblies, 1,85,000 of them will have more variation than what we have defined here. So that will be our rejection. CPK, sigma, or yield percentage. So let's keep it simple. Let's say my target is 99.95. So 0.05 rejection is okay for me. So then this is the target, 99.95. And what I have achieved right now is only 81.48. So then I can go to the contributors and then see what is the impact of each of the contributors. So here I can see that there is 43% from the profile of 0.3. So let's say if I bring this down to 0.2, you can see that the contribution of that particular variable will change because I'm making it more precise. So if I change this one also to 0.2, because it's the same part. So now the yield will increase to 93%. So it has moved from 81 to 93. Because I have the list of contributors, I can see which variable is contributing most towards the assembly variation. And based on that, I can target that particular variable. So like this, I can see all the different variables. Like here we have only 5 parts, so we don't have too many contributors. But when we are working in an assembly with 20, 30, 50 parts, there will have a long list of contributors. So there it will be much more helpful for me to understand which part or which dimension is having more contribution towards this variation and which dimension needs to be controlled. Basically finding out critical to quality dimensions. So if I wanted to further improve on it, I could, again, this is dependent on the manufacturing capabilities, right? So if you have some limitations, let's say the supplier cannot go below 0.1. So obviously in that case, I'll stick with 0.1. I'll not go below that. Now I've achieved 99.5, but my target was 99.95. Now again, if I look at this contributor, the pushing turnout tolerance. So here, if I let's say change it to 0.05, for example, now my result has almost been met. So it is 99.946, very close to 99.95. So like this, I can optimize my tolerances, and then again, if any of the tolerances is too precise, then I can relax the tolerance for that in order to reduce the manufacturing cost. So any questions, queries, please let me know. Yeah, so there are multiple questions here. Let me just take it up one by one. So the most recent question is, only by using worst case boundary, we can ensure 100% perfect assembly. Yes, that's true. If we are designing for worst case, we can ensure that 100% of the assemblies will work. But the probability of having that failure may not be very significant. So for example, the difference between 3 sigma limits or let's say 4 sigma limits and worst case, that may have a huge impact on cost. So for example, if let's say my 4 sigma limit, let's say if you look at it this case only, so there is 0.05% rejection or failure. Now if I design for worst case, my worst case is 0.2 and I'm at 0.1. So the cost between going from 0.1 to 0.2, or in other words, bringing down the worst case within my 0.1 limit, that may increase the cost too much. So for example, if I again look at the contributors. So basically these are all contributing the same amount. So let's say I go to this profile and change it to, let's say, 0.05. So as I'm changing it to 0.05, my worst case has come down to 1.15. Now if I again see what other things I can do, let's say if I look at this runout, let's say if I bring it down to 0.02, if that is possible. Now it has come down to 0.12. So as I'm increasing the precision, I would be able to bring it down in the worst case limits. So my design will be 100% safe, but then the manufacturing cost will also shoot up, right? So that's why statistical variation is used. Like in case of medical industry, where you have class 3 medical devices, where even one rejection is not allowed. If even one medical device fails, it may cause discomfort or harm to the patient, and obviously there may be some legal consequences. So in case of medical, you may want to design for worst case, but for other industries like automotive or electrical, electronics, all that, so their statistical will be more preferred, because that will help you with the optimization of manufacturing costs also, not just the quality. So there is another question about 3D stackup. So see, like here, if I look at this result, here is a message saying that the results are ignoring potentially significant 3D effects. So this message will show up when the inputs that you have given. Like if I look at the inputs here, this profile, okay, this profile tolerance is controlling not just the linear variation of the surface, it is also controlling the angular variation or orientation. Okay, so obviously that is not considered in this case, because this is limited to one-dimensional stackups. So for 3D based stackups, we have to use 𝐶TOL. Okay, so 𝐶TOL is a separate tool. It is not, it does not work as a add-in module in Creo. So that's a separate tool where we can do the complete 3D based analysis, where we can take all those variables into consideration. So like if you want to explore further on the 3D based stackup, like one thing is that anyway we are doing webinars for 𝐶TOL also, so you can join that, or you can just contact me directly, and we can discuss offline how this 𝐶TOL will be helpful for you for your products. Another question is if the separate license required for already installed Creo. Yes, so Creo, the Creo base license will not include this EZ Tol and GD&T Advisor. It has to be added as a separate module. So just like you have, Creo Simulate or Mechanism Dynamics or Tool Design, so these are all separate modules. So similarly, this Creo GD&T Advisor and EZ Tol, both are separate modules. If you have a high-end package, it may be included in that. Otherwise, it has to be added separately. Another question is tolerance stack up for assemblies with welded joints. Right. So if you have welded joints, there will be no variation between the parts. For example, if let's say this top plate and this axle support are welded, so there will be no variation in the position of this part with respect to top plate. But still, we would need to define, let's say, the perpendicularity of this surface, let's say, with respect to this. So there we can define it as a as a perpendicularity, like a geometric tolerance or angular variation. But we have to consider the welded assembly as a single part. So there is an option in Creo called shrink wrap, where you can just shrink wrap the complete welded assembly as a single part, and then introduce that in the assembly. So that way you can, consider it as a single part without any joints. Basically, there are welded joints, so those are not joints which will be moving, right? Fixed joints, basically. So that's how we can work with the welded assemblies. Now there is one question: which type of Creo license are required for MBD? So MBD is basically a process where different tools may be required. So which, like I was talking about this annotation tab earlier. So this annotate tab is used for, adding various, you can say dimensions. And then we also have these tabs at the bottom called combined states. So in MBD, what we can do is we can create different views for the part, like front side, top view, where we can show different dimensions with respect to different views, just like you have it in your drawings. All of that can be defined in Creo 3D part itself, where you will just switch from one tab to another, and then the part will move, with respect to that orientation, like it will show front view with dimensions which are relevant for the front view. Then this other tab, it will show top view and dimensions with respect to that. So that way we can define all the different views with dimensions, and we can put the rest of the information like material specification or tolerance standards, title block and all that. So all the things can be added in 3D itself. There are some options, in this annotation tab which can enable that. Okay, and then obviously you don't have to do it every time. You can save it as a template and then reuse it for all your parts. Okay, so that is with respect to rest of the PMI. Putting aside the GD&T, all the rest of the PMI can be defined through this annotation tab. But for GD&T, obviously GD&T Advisor is the one which is, more suitable because it is more in line with the GD&T standards. So there is, yeah, so there is also one question that if this is a 1D stack up, yes, if this is limited to one-dimensional stack-ups, this EZ Tol is not going to cover 2D or 3D variations. For that, CTOL is the right solution. Okay, so in fact, I have this CTOL also open here. So if you want, I can quickly show you. So for the same assembly, here we have the 3D based results. So what we were looking at earlier, in with respect to that linear variation, like variation in the vertical direction between the two axes, pushing axis. So we have the contributors for that over here, and this Ty variation for the plate thickness, that is a major contributor. But then we also have angular variation of the surface as a contributing 7%. So basically 14% if I combine both of them. 7% from this, 7% from this. So around 14% is there, which is angular variation. So more of a 3D variation, which was excluded from the one-dimensional stack-up results. So obviously that 14% result, accuracy will not be there. And then again, we have angular variation for this hole also. So again, this is contributing around 3.5%. So you can say roughly 20%, you can say roughly the variation is there if we compare 1D versus 3D. So the results that we're getting in 1D are roughly speaking 80% accurate. Okay. Now in 3D, this is the variation which I was talking about. The angular variation of the surface will tilt this part like this. So again, this is what was not included in the EZ Tol, which is covered in CTOL, which is complete 3D based tool. But anyway, I'll not get too much into the details of CTOL. I just wanted to quickly answer that question. So, guys, any other questions? Just check. So there is one more question about showing another example, but we're already past 4 o'clock, so this session was for only for 1 hour, so we cannot show other examples, but if you want me to, talk more about EZ Tol and you want to explore more about how it can be helpful for your product line, so for that, you can reach out to us. Let me just share my information. Okay, so this is my information. You can drop me a mail or give me a call, and we can discuss on how 𝐶TOL, GD&T, whether it is 3D based analysis through 𝐶TOL, 1D analysis through EZ Tol, or GD&T application through GD&T Advisor. So for any of these topics, we can discuss in more detail. Okay, thank you guys for your time. Thank you for joining the session. So we are, not adding too much complexity in our examples so that everybody can understand it. So if you want, want us to help you with your product line, if you want to understand how 𝐶TOL will be helpful or EZ Tol will be helpful for your products, you can just let us know. We can have a separate session and we can explore further on how that can be done. Yeah, so the session is recorded, and if you drop me a mail, I'll make sure that you get the recording for that.